Hello, I'm Alessandro Ronca. I will present temporal logic monitoring rewards via transducers, a joint work with Giuseppe de Giacomo, Marco Favorito, Luca Iocchi, and Fabio Patrizi. In this work, we studied the problem of rewarding an agent for its behavior over time. To give a concrete example, consider the case of a mail delivery agent. This agent has to deliver mail from a post office located on one side of a lake to a town located on the opposite side. The agent is able to go through the lake, but if he does so while carrying mail, the mail gets wet. So we would like the agent to go around the lake. We may consider to give the following rewards. A positive reward when the agent delivers the mail without going through the lake. A very negative reward when the mail gets wet, so when the agent crosses the lake while carrying mail. And a negative reward at any instant before the delivery, so the agent tries to deliver mail as quick as possible. The important thing to notice here is that each reward condition refers to an extended period of time. In the paper, we present monitoring rewards, which improve on existing temporal logic specifications for rewards. Particularly, they allow for a better control over reward assignment at no additional cost. We also argue that reward transducers are a more convenient formalism than acceptors whenever one is not interested in the source of rewards. I will first present some background. The problem can be formalized using as a decision process with non-Markovian rewards, which consists of a finite set of states, a finite set of actions, a Markovian transition function, and a non-Markovian reward function. So while the transition function depends just on the last state and action, the reward function depends on the entire history, the entire history of states and actions. So it maps each trace consisting of states and actions to a reward. And if you consider another trace, which is almost identical to the previous one, in particular, the last elements are the same, but one of the past elements is different. Let's say that S2 is now replaced by S prime. We have that these trace can be mapped to a different reward R prime. The formalism that we extend is the one of temporal logic specifications of non-Markovian rewards. In particular, specifications where the reward condition is given as a formula in linear temporal logic on finite traces or linear dynamic logic on finite traces. The other component of the specification is the reward that we want to issue whenever the formula is satisfied. In fact, given the partial trace generated so far by the agent interacting with the environment, we check whether the reward condition 5 is satisfied in this trace, and if so, we issue the reward. The nice thing about temporal specifications, and in particular about decision processes with rewards expressed as temporal specifications, is that they can be encoded into a Markov decision process. To do so, we first have to compute the deterministic finite automaton for the reward condition, and then we combine this with the transition function of the initial decision process to obtain a new decision process, which now is fully Markovian, at the cost of an extended state space. The state space now is made of component coming from the original decision process and a component coming from the deterministic automaton. I will now introduce monitoring rewards, which are the main contribution of our paper. They are an extension of temporal logic specifications of rewards. And in fact, the idea is to still have one reward condition, but to assign different rewards based on the way this formula is satisfied. In particular, now we have 4 values that we want to issue based on the different ways in which the formula is satisfied. These conditions come from monitoring. So now we don't look at whether the formula is simply true or false, but we look at whether the formula is temporarily true, permanently true, and temporarily false or permanently false. For instance, a formula is temporarily true if it is true in the current trace, and there's still a way to make it false. So there is an extension of this trace that makes the formula false. In the other case, we say, so if there's no such an extension, we say that the formula is permanently true. The way these monitoring rewards work is that given the current trace, we check whether it is temporarily true, temporarily false, and so on, and we issue the corresponding value. So for instance, if the formula is temporarily true, we issue reward R. If the formula is instead temporarily false, we issue C. Going back to the example of the mail delivery agent, the task of the agent can be captured by the formula not lake until delivery, meaning that the agent shouldn't go through the lake until it delivers. And we can build a monitoring reward based on this condition, which assigns -1 when the formula is temporarily false, +1 when it is permanently true, and -10 when it is permanently false. The value 0, so the value to assign when the formula is temporarily true, in this case plays no role because this formula is never temporarily true. Now we have that if the agent moves to a cell that doesn't correspond to the lake, it gets -1 because the formula is temporarily false. And he keeps getting -1 for each move of this kind till he reaches the delivery point, which at this point he makes the formula permanently true and he gets +1. Now let's consider another run in which the agent goes directly into the lake. By doing so, the agent makes the formula permanently false. So the agent gets assigned -10. He gets assigned -10 if he keeps moving through the lake, but also if he keeps now moving through the land. And he gets -10 even if he reaches the delivery point, because the formula cannot, if it's permanently false, cannot become true under any circumstance. In the paper, we show how to realize monitoring rewards by making use of transducers. So let's consider a monitoring reward where, as I said before, the reward condition is specified in linear temporal logic on finite traces or linear dynamic logic on finite traces. This reward, the reward condition can be the monitoring conditions over this formula phi can be captured by 4 LDLF formulas. So we can use these 4 formulas, phi r, phi c, phi s, and phi f, to build 4 temporal logic specifications for rewards. Then these 4 specifications can be translated into deterministic finite automata, so into deterministic finite state automata, which can be used to check whether the condition is true, and whenever the condition is true, so the automaton is in a finite state, we can issue the reward. In the paper, we went further and we improved this construction. We did so by using reward transducers, which are transducers that map partial traces to rewards. We have 2 versions. We have the more machine version, which consists of a finite set of states, an input alphabet of states and actions, because at each step the machine reads a state, an MDP state, and an action. And then we have, as the output alphabet, we have a finite set of rewards, the rewards we want to issue, the initial state we have, a deterministic transition function, and the output function that maps each state of the machine to a reward. We also have the mini-machine version, which is almost identical except for the fact that the output function depends also on the input symbol. However, in the rest of the presentation, I will focus on more machines since our constructions are not really different for the two cases. So going back to the construction I've shown before, we have shown how the monitoring reward can be realized by 4 acceptors, which tell you when to issue one of the values. However, these 4 values can be included directly into the corresponding machine. And this way we obtain 4 reward transducers. Here, the important fact is that these 4 transducers have the same shape, in the sense that they have the same set of states, initial state, transitions, and so on. The only thing that in which they differ is the output function. So we can easily combine them into one transducer by taking the sum of the output functions of the four transducers. And this reward transducer now directly implements the initial monitoring reward. In the case of the mail delivery agent, we can first compute a transducer that outputs -1 whenever the formula is temporally false, a transducer that outputs +1 whenever the formula is permanently true, and a transducer that outputs -10 whenever the formula is permanently false. We can also consider the transducer for the case in which the formula is temporally true. However, this transducer does not put anything because the formula is never temporally true. And these 4 transducers have the same shape and can be easily combined into one transducer, which directly implements the monitoring reward and is not bigger than any of the initial transducers. In our work, we decided to work with transducers that directly represent reward functions. An alternative is to work with acceptors. In this case, each acceptor tells us when a reward condition is satisfied, and then based on this, we have to issue the corresponding reward. However, if you're not interested in the source of rewards, reward transducers are better than acceptors. We can easily combine multiple transducers into one transducer by taking, for example, the sum, as we did in our work. And this allows us in general to save states. In fact, in the case of monitoring rewards, by merging the 4 acceptors by transducers, we don't get an increase in the number of states. As it was done in the case of temporal logic specifications, also in our case, we can compile the Markov decision process with monitoring rewards into a simple Markov decision process, a standard one, fully Markovian, so both the transition function and the reward function are Markovian, at the cost of increasing the state space, which is obtained by taking the cross product of the original states of the decision process with the states of the transducer. To conclude, we have presented monitoring rewards, which improve on existing temporal logic specifications for reward, that allow better control over reward assignment and no additional cost, in the sense that the Markov decision process we obtain at the end has no additional states compared to the previous approach for temporal logic specifications. As the next step, we would like to focus on reinforcement learning. So to study agents that learn to behave optimally under non-Markovian rewards, but this time without the help of the extended state space. And we would also like to look at reinforcement learning in the case of non-Markovian rewards and non-Markovian transitions.